So everyone tells me I should go outside more. So this is officially me going outside, which is why you might be able to hear some kind of insect in the background. But it officially counts as being outside even though I'm still playing on my computer. So we are going to look at the Towers of Hanoi. It's kind of this old like toy thing. And the idea is you want to move everything from the first tower to like the last tower in the minimum number of steps. And once you figure it out, it's kind of a trick to it. It was actually one of the first computer games I had, and it was like this text-based thing where you like typed in A and then you typed in C and then it moved it from A to C. But basically the idea is like I can take this little dude and I can put him here. All right, and then I can take this dude and I can put him here. And you can play, there's like a million games like this online that you can just download and play with. So you can kind of get the theory. And then this one goes here. And come here, girl. And then this one goes here, and then this one goes here, and then this one goes here, and then this one goes here. And you're like, yay, I did it. Okay, so if you were counting, that took 7 steps because I was like here to here, and then 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 here to here. So that's 1, 2. That's funny. Let's try this again. I did 1, 2, 3, 4, 5, 6, 7. All right, so that was 7. That was 7 steps. You can pause it and rewind it and look at it again, but it was 7 steps. So the question is, how does this work? How can I but know the minimum number of steps? And it's actually super easy because it's a recursion. And there's a pattern to it. So I recommend that if you've never played with this game, that you go kind of mess around with it. Because once you get the pattern, it makes sense. But if you don't get the pattern, then this whole thing we're talking about isn't going to make sense. So I decided that outside was dumb, and we moved back inside. Because why would you want to go outside when you have a perfectly lovely inside? Okay, so again, the idea that it's recursive, and this is not really meant to be an introduction to the concept of recursion, just on like how to mathematize recursion. So the idea is if you want to explain to someone how to solve this problem, you would say, okay, so the first thing is if you have, say, n disks. If you have n disks, what you want to do is you want to move n minus 1 disks. I can't spell. N minus 1 disks. And then you want to move disk n. And then you want to move n minus 1 disks back. And that kind of seems dumb maybe. So let me see if I can try and illustrate. All right, so we've got 3 disks. Now the way that the algorithm goes is, all right, so if I could just do it this way, I could say, okay, I have 3 disks. So I want to move, so I have 3. And so I want to move 2 and then move number 3, and we're labeling them 1, 2, and 3 like that. So I need to move number 3, and then I need to move 2 back. Okay, so what we're going to do is we're going to come in here. We're going to say, okay, so I have 3 disks. I'm going to move 2 of them away. Now, this is a totally illegal move, but I'm going to move 2 of them away. And then I'm going to move this one. And then I'm going to move the 2 back. And you're like, super easy. Yay, why don't I just do that? Well, because you can't, because that's illegal. So in order to move those 2, I had to do an illegal move. Come back. So I have to think about it a little bit more. And this is where the recursion comes in. So it's like, okay, so I have 3 and I want to move 2, but I can't actually move 2. So now I have to start a new problem where I have 2, which means I want to move 1 and then move number 2 and then move 1 back. I don't know if you can see that. All right. So I'm going to move 1 and then I'm going to move number 2 and I'm going to move 1 back. So, all right. So I can do this. I can move 1 and then I can move number 2 and then I can move number 1 back. All right. So officially completed these 3 steps, which was moving that step. Now I can, in fact, move number 3 by itself because he's cool with it. And all right. And so I've done that. But now, again, to move 2 again, I have to do this again. I'm in the same situation. I'm just not going to rewrite it, except I lost my ends. All right, so to move the 2 back, first of all, this is where the recursion comes in. So I have 2, which means I have to move 1, and then I can move disk number 2, and then I can move 1 back. And then I finish that, and then I'm good to go. Okay, so again, the idea is, if you have 4, then you have to move 3, and then that puts you here. So yeah, so the more disks you have, the more steps that you have to take to do it. Okay, so that was kind of our introduction to the Towers of Hanoi. Now the fun part is, if you like math, the fun part is guessing, or not guessing, but determining in advance how many steps this is going to take. So what we're going to do is we're going to find a number, t sub n, to be the number of steps that it takes to move n disks. Now we probably start with t sub 1, which makes sense. T sub 1, it makes sense. It would take 1 move to move 1 disk. Based on what we were just doing above, t sub 2, it takes 3 steps to move, because if you've got troop to 2, you move 2 disks. So this one goes here, this one goes here, and this one goes here. So that's 3 steps. So t sub 2 is 3 steps. T sub 3 is 7. Now we can keep doing this, and I can go ahead and give you some more of these numbers. 4 disks takes 15 steps. 5 disks takes 31 steps. 6 disks takes 63 steps. Okay, now the idea is, so we have an idea that if I do know my definition of the steps, of the algorithm at least, not the number of steps. But what I'm trying to get is, my goal here is to get a closed form. I can't spell. Closed form. And a closed form is basically just a fancy word for a formula. So like I want to have like t sub n is equal to n squared plus 2n plus 5 or something like that. Like I want a closed form. Because what I can do with my steps that I have, so I can actually get a not closed form by saying, okay, so if I want to move n minus 1 disks, that takes t sub n minus 1 steps. To move disk n takes 1 step. And to move n minus 1 disks back takes t sub n minus 1 again. So what I have is a recursive formula where I can say, well, the number of steps to move n is equal to, if I add all these together, 2t n minus 1 plus 1. Okay? And yay. Now, technically, it's not a recursive definition unless I have a validity and unless I have a starting point. So actually, we can start off by saying t sub 0 is 0. It takes 0 steps to go to move 0 disks. So the recursive definition would be this, t equals 0, and n is greater than or equal to 1. And if we really want to get fancy, we can say n is an element of the positive integers. That's another good thing that we could do because it doesn't really make sense for non-integers. Anyway, so this is a recursive formula. And if you check it out, you can kind of see that this makes sense. So this 1 would be 2 times 0 plus 1. This one would be 2 times 3, or sorry, 2 times 2. Man, science. By science, I mean, let's try this again. So this one I've got 2 times, let's do it this way, the 0 plus 1, and that gives me 1. And then I have 2 times 1 plus 1, and that gives me 3. 2 times 3 plus 1, and that gives me 7. And so I can tell that this does match, and it should, because I logicked through it. So I got my base case. By the way, this is called your base case. I got my base case, I got my recurrence formula, my recursive formula, everything's good. So all is well until I want to figure out what is t sub 876, because the only way to get it is to say, well, that's 2 times t 875 plus 1, and then I have to figure this out. So the big goal here is to actually get a closed form for doing this. Now, there's a lot of different ways to do this, and I think I've got other videos on how to do this, like kind of the long and hard way. But if you want to be a true mathematician, you're just going to listen to your gut. And the gut is just to look at it and go, man, this pattern looks familiar, and I'm not exactly sure why. Okay, so one of your hints might be the fact that we keep 2 times 2 times 2 times 2 times. And if we're 2 times 2 times 2 times 2 times 2, maybe that like brings to mind something like an exponent. The plus 1 is a little misleading because instead of being a plus 1 in our closed form, it actually ends up being a minus 1. But for the purposes of this video, the idea is that you would be able to kind of look at this after a while and go, you know what? I think that this t sub n is actually equal to 2 to the n minus 1. Because if you look at this, t to the n, or 2 to the n, this one would be 2, 4, 8, 16, 32, 64. So this is 2 to the n. So if you just kind of subtract 1 from all those, you could see it. So this is what we're going to call flash of inspiration time. Not because you necessarily have to do that. That's just kind of what we're, I guess, assuming. Like I said, there's harder ways to do it for sure. I just figured let's pretend we figured it out. We're pretty sure it's right. It works for every example that we have, but we would like to make sure that it's right. And this actually doesn't take that long to do. We can actually use proof by induction, and I can show you how to do that right quick. All right, so this is how proof by induction works. And apparently my writing is very, very angly. Woo, this is an acute angle. The idea is what you're going to do is demonstrate that your guess works for a base case like n equals 0. Then we're going to show that if we assume it works for k, then it also has to work for k plus 1. So like if we say that it works for n equals 0, okay, then we show, well, if we assume it works for k, it has to work for k plus 1, which means since we showed it worked for n equals 0, it has to work for 1. Now that we showed it work for 1, it has to work for 2. Now that we showed it work for 2, it has to work for 3. So theoretically, I have people who say you can prove that proof by induction works using proof by induction, and I've never cared enough to ask them to show that to me, but it's a thing. Okay, so we're going to do this proof by induction on our little guess. So the first step is to demonstrate that it works for a base case. So we want to know, is t sub 0, is that going to be equal to 2 to the 0 minus 1? And that's 1 minus 1 and is equal to 1, so yes. All right, so that step was easy. Now the second step is to show that if we assume that it works for k, so we're going to assume it for k. So we're going to assume that it's true that t sub k is equal to 2 to the k minus 1, all right? So that is our assumption. Now our question is to show that t sub k plus 1 is equal to 2 to the k plus, not 2 to the k, yes, is equal to 2 to the k plus 1 minus 1. So that's our goal. Now we know, I feel like changing colors, we know that t sub k is equal to 2 t sub k minus plus 1. This was our recursive. So cos recursive. Okay. And we also could just as easily say, replace all of our k's with k plus 1. So 2tk plus 1 plus 1. Oh, I did that wrong. Boop, boop. Better? Yes. Okay. So we know that both of these are true. So this is true because recursive. This is true because I didn't make a typo at all, I swear. Okay. Now we have this assumption. And we can take assumption and we can put assumption here. Okay, so we know that t sub k is equal to 2 to the k minus 1, because that was an assumption, plus 1. We can keep doing the math. 2k plus 1 minus 2 plus 1. So now we have that t sub k plus 1 is equal to 2 to the k plus 1 minus 1, which was our goal. And then we write QED, which is Latin for mic drop. Actually, it's something like, so it is demonstrated, or something like that. But basically, that's how we're able to prove that that's exactly what we were trying to do. Okay, so in case you're wondering why we were looking at this, what are we supposed to learn from all this? So the first thing you're supposed to learn is to look at small cases. The way that this got, easier is by not trying to figure it out from the T876 thing, but to kind of look at the small bases, and not just to look at to the 1, but also to go all the way down to the t equals 0, or the n equals 0 case, and see if that helped us clarify. So as a mathematician, it's important to always look at small cases. The next step is to find and prove a recurrence relation. A lot of times things are easy to kind of explain recursively, like the whole, well, if I have 3, I got to solve the 2, and to solve the 2, I've got to solve the 1. There's a lot of things that act like recurrences, and they're pretty easy, sometimes-ish, to verbalize. And so by finding and proving the recurrence relation, I knew that I had something to start with. And then the last one is just to find and prove a closed form expression. So the finding is the hard part, and like I've got lots of videos that talk about all kinds of different ways to do that. The finding is the hard part. The proving usually isn't too bad as long as you've got a solid recurrence relation. Usually you can just do this by proof by induction, and that ends up being actually not that bad. But this was really not meant to be like a super crazy getting into recurrence relations, because it definitely goes deeper than this. This is really just meant to be like a, hey, yay, recurrences aren't that bad. Let's have fun. It's not scary yet.